Physics, engineering. I'm an engineer. Mhm. So yeah, thank you for having me at the seminar. I will tell you a little bit of the work I did for my master thesis. Uh, so I want to start. Ooh, perfect. I want to start by thanking just my advisor, Giuseppe, who I believe gave a talk also here a while ago, Pedro, and Nadir, who was a postdoc at the time and was also very involved with the project, and he helped me out during the thesis. So a little menu for the day. I'll start. My work has a bit of overlap with last week's talk from Angelo. Still, I try to make it self-contained. So if you weren't here, should be okay. But feel free to ask any question if something's not clear. Start with a little introduction on what are measurement-induced phase transitions and some interesting physical interpretations that people have found and connections to more classical condensed matter theory. Then I'll explain what model I studied specifically for the thesis. I'll discuss a bit how we numerically try to identify the transition point, because as I will explain, it's a bit hard to do for this type of monitored systems. And then I'll discuss a bit the measurement records that are in the title and some conclusions and I guess open questions and future directions. So to start out, like Angelo discussed last week, what I studied were monitored systems, which are sort of the interface of closed systems and open. So you can think of them as a combination of a unitary evolution generated, for example, by a Hamiltonian, interrupted by some measurement events. And a way that you can kind of intuit it, that there might be a transition in this setup, is that in general, these operations do not commute, and when you have non-commuting operators competing, you can think, for example, of two non-commuting terms in an Hamiltonian. In this case, they will compete for the steady state behavior of the system. You can expect to have a crossover or a phase transition, which in this case will turn out to be a real phase transition. So observables in these type of systems follow what are called quantum trajectories. So they have periods of smooth evolution followed by sudden quantum jumps. However, for example, here I plot a single trajectory, but the observable could have jumped to another value if the measurement outcome was different. And this leads to a large amount of possible trajectories, which grows exponentially with system size and time. And since a feature of these transitions is also that they are really physics contained in the trajectories and not in the average dynamics, this becomes a problem because you need observables that have some information about the trajectories. The most common approach is to use nonlinear observables, for example, the entanglement entropy, where clearly if you average per trajectory, if you average before computing the entanglement or after, this gives you a different result. And clearly the left side has some information about the trajectory dynamics. These sort of transitions were first observed in random quantum circuits. So these blue blocks, you can choose to be your favorite unitary ensemble. And then you place some measurement operators. These white balls correspond to projective measurements, which you place with a probability p. And turns out that you have, as you increase p, you have a genuine phase transition from a volume law to an area law, and at the critical point, you have all the things you expect from a critical theory, and you have a logarithmic entanglement scaling. So this was how these transitions were first observed, was in the scaling of the entanglement. However, since then, some nice, okay, just because it's a lot, some nice physical pictures have arisen. For example, this purification picture. This is the same transition. The critical point will be the same. If you start with a reference with a larger system that it has some entanglement amongst these two partitions, and then you evolve one of them with one of these random circuits with measurements, there is a transition from a phase where there is the state only purifies at infinitely large time, so you have no more sorry, an exponentially large time with system size, so you don't have entanglement anymore. And then if you increase the measurement rate, eventually this will purify in log depth. Another nice interpretation, more recent, is on the learnability side. So if you think that you want to encode some information, you start with your initial state, you encode it with some unitary, and then you run it through one of these monitored circuits. What people call this learnability transition is whether Eve, so an observer that has access to these measurement outcomes, can learn anything about the state you encoded. For example, if you start with let's say your task is to distinguish two orthogonal states that you encode, either state A or state B. In the low measurement phase, Eve cannot do better than random guessing, so it's 50-50. However, once you go to the high measurement phase, she can do a little bit better than random guessing. This, I think, is a nice picture because it relates it to some actual quantum information applications, and also connects a bit with the error correction picture that Angelo mentioned last week. Another nice connection, a bit more less with less application, but is that you can map these random circuits with measurements to classical, between quotation marks, statistical mechanics models using these Van Garten techniques. If you're familiar, I know some people work with this, and you are left with basically a classical spin lattice, which people have been studying for a long time. So there's a lot of results on this, and you can make strong statements about the phases of these information phases of the circuit based on the what you see in the lattice model. But this is in circuits. However, when I introduced, I showed you Hamiltonian evolution. So I mean, it's a natural place to look. Also, what happens if you have instead a Hamiltonian system evolving combined with measurement? The simplest case you can look at is just a fermion hopping on a lattice, and you perform projective measurements randomly on the sites. This is I would say the most widely studied model of these monitored Hamiltonian systems, and it led to a lot of back and forward on whether the transition existed or not. Initially, people thought there was a transition from a critically extended phase to an area law. So here is a bit different. You don't have volume law, but it turns out that in fact this critically extended phase is not stable to measurement, and as soon as you start measuring, you go to an area law, but the correlation length is exponentially large as you can see in the inverse monitoring rate. So this makes these systems very hard to study numerically, which will come up again later, but just to keep in mind. So this system does not have a measurement-induced transition, at least in one dimension. But we want to study measurement-induced transition, so how can you restore this the stability of this phase? Yeah? Gamma is the measurement rate. So in this case, depends a bit on the unraveling you choose, but you can think of it, for example, as I mean, I think in photonics often they do this homodyne detection, right? Usually I think more of it in projective measurement. So you can couple these maybe to a registry, and then if you measure the registry and it comes out as 0, you do a no-click step, and if it comes back as 1, you say that there was a jump event, and you can, under some small assumptions, derive Krauss operators that give you, I mean, the evolution with this Hamiltonian, and then interspread with this jump operator. Sorry, here I used eta. This I took from another paper, that's why, because eta is what I use for the rest of the presentation. Yeah, eta is gamma, sorry. Yeah, but yeah, that's basically it. From now on, I think, yeah, I will mention if there is a gamma that is not a monitoring rate. But yeah, okay, so moving on, how can you, yeah? Um, I think, so if you do local measurement operators, this is the only, I mean, okay, no, it's not the only thing, but it's like, um, I guess the most obvious one, for example, if you do particle loss, because this is number conserving, you'll just go to the vacuum. I don't know, you can engineer some weird measurement operators that will give you some, I don't think you can get an extended phase. I've not seen any work on this, but you can get specific points where you have different properties connected to some exceptional points of these of the effective Hamiltonian that I'll explain a bit what is in a couple of slides. And if you do non-local measurement, you can also restore I think you can even get volume law entanglement. But yeah. Yeah, so you monitor every site, but only one jump at a time. So it's a local measurement. Only one site is measured. Mm-hmm. Yeah, this is an assumption you make. So I guess maybe if I explain, so how you simulate this, you do a bunch of steps and you keep, you use the Born probability, so the local occupation to measure how much probability there is to be a jump. And you sample a random number. If it's under this probability, you have a jump at that site. You can do like a cumulative over all sites. But one assumption is that only one happens in time. Of course, then when you take the thermodynamic limit, it's a bit weird, but so only one site. Uh, okay, this is the setup of that Angelo discussed last week. So what you get is if you don't have, I think if you have an extensive number of sites being monitored, you go to this area law, but otherwise you get volume law entanglement. I'm not sure if there's a. Mm-hmm. Yeah, it's a. Yeah, this measurement uh, here is not really the case because you have particle number conservation, but you can imagine kind of like if you have a photon setup, let's say, like when there is a photon emission, that's how what you call a jump. So here would be a different physical implementation because you cannot lose particles, but this will happen for all the time. That's the assumption. If you stop measuring, you'll just get a quench, right, and you'll go to volume law entanglement.
So when you mentioned no local versus no local, you meant, for example, like having an entangling measurement. That's what you meant for non-local?
No, by non-local I mean really. I mean I don't know how if these measurements are physical, but I've seen some works where people do this diffusive unraveling. So you make a weak measurement, but instead of being those hard jumps, you'll just get some noise on the trajectory, and there they consider really like polynomially decaying tails of the measurement operator, but I never saw anyone discuss how you can implement it. Maybe there is a way. I'm not super familiar with that. That's what I meant. If you do this entangling measurement, like a two-site measurement, you can get non-trivial no-click operators, which can give interesting physics. But as far as I know, you cannot get the extended entangled phase. It seems to really not be stable. It is still, I think now there is some consensus with these very large numerics, and there's some field theory predictions, but it wasn't clear. I think it's a very recent thing that there is a consensus. So we were asking how to get, I guess, extended entangled phases. There's a couple ways. You can add interactions, and this will restore a phase diagram much more similar to what you saw in the circuit. So you have a volume law to an area law transition. Yeah, and you can also go to higher dimensions if you. If you consider, for example, a lattice in 2 dimensions instead, there is already a measurement-induced transition. I think an intuitive, maybe intuitive is a strong word, but a way to understand this is if you are familiar with Anderson localization, you can think of this type of transitions as localization in space and time. So you can think of it as an Anderson transition in d+1 dimensions. So for Anderson, you only get a transition in 3D. Here you get in 2D, and in 1D is like a borderline, like it would be in 2D. I mean, it's not exactly the same transition, but I think it's a useful mental picture. Okay, then a third way is to break the U1 symmetry into Z2 by adding these pairing terms, for example. And this is the model I chose to study for the thesis. I parameterize it in this way because you can, by Jordan-Wigner, interpret this as a spin chain with different couplings in the X and Y direction in the external magnetic field. And this model with local monitoring does sustain an extended log L phase, and at a finite rate it transitions to area law. So specifically the monitoring protocol I'm considering is that where I have, again, like I was saying, there's a registry. So I'm interested in monitoring the upspin state, like you see here. And basically what happens is that since I'm not performing a projective measurement, I'm only monitoring the upspin state. This leads to some measurement back action, which gives us a non-trivial effective Hamiltonian that I was discussing before. And another reason why we chose to look at this unraveling. Yeah, so basically this will have that picture of smooth evolution generated by this effective Hamiltonian interrupted by projective jumps where our spin, here in this case I chose to point down, but it is up to parameterization or to how you choose to do the transformation. Okay, and before I proceed, just a little intermezzo to give you some notation on Gaussian states in case you're not very familiar. The idea is this Hamiltonian is quadratic, so you can map everything to a smaller dimensional space. So instead of dense matrices, I will work with this key. Instead of Hamiltonian, I'll work with this calligraphic H, and this is reduces your space from an exponential size to polynomial size, which allows for numerical simulations, also some nice algebraic things. So using this, as you see, we can diagonalize the Hamiltonian, assuming that is periodic, and we get that spectrum, which is a complex spectrum. So you have some decay that is coming from this measurement back action that I mentioned. And turns out that this Hamiltonian has a non-trivial phase. So here I'm not, there is no measurements, but already as you increase the monitoring rate, you see a change in the in this generator of the no-click dynamics. So that ellipse is what separates the phases. Inside the ellipse, you have a log L entanglement, which is connected with the imaginary part being gapless. And then when you go outside the ellipse, the gap opens up in the imaginary part, and the ground state of this effective Hamiltonian becomes area law. And this is not a rigorous connection, but one of the assumptions of the work. And as I will explain to you, there is some reasons to think it holds, is that this phase diagram is the same as the one of the full monitor dynamics. So if I add jumps as well, that this ellipse remains stable. Yeah, so here is just, so here's the real part, complex part. The real part doesn't matter too much here. What matters is whether the complex part is gapped or not. And you see the blue line is gapless. The red should be gapless. I mean, there's a little uncertainty, but it's right at the transition. And then outside, you always have area law. So you can drive the transition with a monitoring rate or with a magnetic field. But in general, I'll focus on the monitoring rate and specifically on the line of h equals 0. So from now on, expect the transition to be at eta equals 4. and rescale by this parameter. I will set everything to 1. Yeah, okay. Sorry, this is maybe bad parameterization. So the gamma here is the anisotropy of the, so how much you break the U1 symmetry, and the J is just the coupling. I think it's not that is integral, is that is non-interacting, is what makes the difference. So as far as I'm aware from the literature, if you have an interacting model, for example, an XXZ chain with monitoring, it will be volume law already, even though it's integrable. But this Gaussian manifold seems really to have to not support or be very sensitive to measurements, at least in one dimension. Yeah. Okay, so I was saying why maybe it's why it's not completely ludicrous to claim that the phase transition or the phase diagram of the monitor dynamics will be the same as as of the no-click Hamiltonian. So this picture I took from this phenomenological paper by Turkeshi. Basically, the idea is just that you assume that the entanglement is generated by quasi-particles. It's a classical way to sort of approximate entanglement generation. And since this will have a complex spectrum, they will have a finite lifetime. And so you assume that you have some entanglement generation for a while, then the particle decays coming from the the imaginary part of the spectrum, and this you associate with a measurement event, and then another quasi-particle is created, and they, with this phenomenological theory, they predict that the transition should be at the same point. Also, there's some numerical evidence here. On the top, you see just for the diffusive unraveling, so weak measurement, but has the same no-click Hamiltonian, and you see that they seem to match. And this is a second paper, which is unraveling very similar to the one I considered. And as far as I know, is the only numerical evidence of where they seem to really agree, and they don't seem to have too many problems with finite size effects. But I think this is explained because this observable they put here is related to the full counting statistics of the X spins, and it's exponentially hard to compute with this system size. So it kind of breaks this advantage that we got by going to Gaussian states, and hence why they only go to L22. So it's not practical to keep scaling up. And one of the objectives of the work, besides looking at measurement records, was trying to find better observables to detect this transition. So how people generally or first looked at it was through the entanglement entropy. So here I'll take different subchain sizes, and I will average at late times just to get because I mean there will be fluctuations. What we see is not clear all from here, but you can see that for eta equals 8, so very high monitoring rate, we have a flat curve, and for eta equals 1 or 2, the entanglement entropy is growing with the system size logarithmically. So you can see there. I chose that sign fit because to handle finite size effects better, but this makes it very hard to see the transition point. So what we attempted to do was look at the entanglement Hamiltonian, which so this is, you can think of it as the reduced density matrix, but the Gaussian version. So it is a subsystem A, and it's our reduced density matrix. We'll look at these R statistics, which is just some way to wash out microscopic details of our model and try to get some universal behavior. And the main idea of looking at these entanglement Hamiltonians is that they, if you look at this special type of spectral quantities, they may follow random matrix predictions. So on the left, for the low monitoring rate, it matches what is known as the GUE ensemble. It's not relevant, but associated with chaotic spectra. And on the right, you see it matches Poissonian, which is associated with integral spectra. This is a nice quantity because you can try to do finite size scaling, like trying to collapse the different curves. It usually shows a crossing. However, for this specific model, we ran into some issues. That is, this is true in the bulk of the spectrum, but not if I consider the whole spectrum. And this bulk doesn't have enough eigenvalues for it to be physically relevant. I think this is due to finite size effect, as I will show you here. So, yeah. No, I think this is not clear whether it is the same symmetry as the initial Hamiltonian, but I don't know if there is a one-to-one connection. If it's an open question, what the symmetry of the initial Hamiltonian tells you. And I think the measurement alters because I look at some other unravelings where you have a GOE Hamiltonian, and once you add the measurements, it breaks this symmetry and it goes to GOE again. So yeah, maybe I should have cleared up, but I'm doing this over the ensemble of trajectories, right? I have a lot of these subsystem correlation matrices, and I do statistics with it. Yeah. Low monitoring rate, so you should be in the critical phase. Yeah. Critical extended, right? Because you have you don't have a volume law, you have a log law for a. So yeah.
I are a collection of eigenvalues. II are eigenvalues, right?
So
tilde is one value for each.
So you lose two eigenvalues, I think one on each edge, but basically the epsilons are the eigenvalues of the entanglement Hamiltonian. So that, yeah, and then you do this, so for each, I guess, two eigenvalues have one value of R. I mean, it's like a,
So you have a collection
of yeah, exactly. Mm-hmm.
And are I tilde is the smallest?
No, it's just so it's between 0 and 1. So you see these distributions are between 0 and 1. Yeah, so R tilde is just. So here, yeah, that's what I was trying to get across. Maybe it wasn't super clear. Ideally, you'd want to do this with the whole entanglement spectrum. And I think it's possible if we go up to larger system sizes. But for these cases, this is in the bulk. So I take a slice of my spectrum and I compute these gaps there. And then what I was mentioning, why this part has a area law of eigenvalues, so it doesn't grow with system size. So I think, and what I'm trying to do now is maybe trying to find a physical cutoff where we still have an extensive, or at least a number of eigenvalues that grows with system size and shows this good agreement with universal predictions. Because, okay, from these I can generate some curves and collapse, but it's not, I don't think it's physical because I don't have enough eigenvalues and it's very sensitive to the part of the bulk I choose. But this approach has been successful in some other monitored systems. I mean, this was kind of, we tried it because maybe it captures more things than the entanglement entropy alone. Yeah. Mm-hmm.
IA is the reduced eigenstates at equilibrium. So when you reach
stationarity, yeah.
And then given a fixed value of the value. And that what we are seeing is a picture of this sort of spectrum coded value of RT. So basically, it's a collection of value.
Yeah.
As large as you possibly can.
Yeah, so here is system size 28, so I go up to half chain, so 64.
And you expect, you want to compare it what is the definition behind having a Poissonian rather than
I mean, I guess the Poissonian, usually how the think there are not many people have looked at these things. There's one paper looking at this in monitor system, and they claim that Poissonian means localized phase, GUE means ergodic. I think maybe it's a bit of a strong statement, but I think the idea is that as if you measure a lot, your eigenvalues of the matrix become independent because I mean they're not related. While if you propagate with a Hamiltonian, they will yeah, generate entanglement. Yeah, and yeah. So
correlation.
in your eigenvalues and they repulse a bit. That's kind of the idea, but I don't think there's a very like obvious reason to look at it just because it's an entanglement quantity, right? This has been used to identify other phase transitions. Yeah. What I was mentioning before about the sort of the cutoffs. So to explain a bit the spectrum here, again, it's these two extreme values. So on the top is the low monitoring rate, and on the bottom the high monitoring rate. And these lines are the predictions of the GUE and the Poissonian, and are the mean values, which is usually what people use to study these things. And as you see, as I decrease the range of epsilons, here, sorry for the different notation, the agreement becomes better, but even for the whole spectrum, so the yellow line is the whole spectrum, there seems to be a convergence, but is much slower. So that's why I say that I think for larger system size, maybe this convergence is something I'm trying to do, but it requires a bit more fancy numerics. So yeah, I'm working on that, but I think it could be a promising approach because there is still no observable that's easy to compute. It's relatively easy that doesn't suffer a lot of these finite size effect issues. Because I mean, ideally, we could really confirm that is the same phase diagram as the no-click Hamiltonian. So here, the other arguments are not 100% rigorous. So now moving on to the measurement records, which I mentioned in the title. The idea was to think of what do we have accessible when we perform an experiment in this type of systems. So in general, computing the entanglement entropy of this trajectory is not possible because you need at least 2 copies of the same trajectory, and they are exponentially rare. So what you do have very naturally much so access is the series of measurements, right? So this M has the history of the trajectory. So basically, this would mean that you had a jump at site 1, at site I1 at time T1, then a jump at site I2 at time T2, and you have a time series like this for each trajectory. And a natural quantity to try and extract from here is what are called waiting time distributions. Here I use this super operator notation just because it makes the formula a bit cleaner, but it's just this L0 is our no-click propagator, which has the spectral transition, and this is our jump operator. And this is the, as you can see, basically this measures the norm decay due to the jump, the propagation, and the other jump, which is connected with the probability that this event may have occurred. Due to kind of Gaussian and free Fermion magic, you can compute this analytically in this case, and you can find this formula, which basically you see that you have a multiplicative term pi 0 that is just the decay of the wave function evolving with this no-click Hamiltonian. Then you have some correction, and only that C term depends on the spatial resolution. What we observe is that this pi 0 term dominates very heavily. As you can see, the exponential with the L there. And so we'll focus on that. And we have an analytic formula for it, but it's not easy to make statements. So you can expand at short times and large time behaviors. Here at short times, it basically looks like a Poissonian because you just have a linear term in the exponent. But at long times, it has a dependence on the imaginary part of the spectrum, the thing that had the transition exactly. So you expect this quantity to be able to see the transition, at least in the no-click Hamiltonian. Here is the plot of the survival probability with a time rescaled. You see that the inset I try is kind of the probability region we have access to if I run the numerical simulations. And you see that there is nothing, from here it's not easy to see anything, but yeah.
Remind me again, what's the difference by zero? By zero, the survival probability.
Sorry, can you?
So by zero is the surviving probability.
Yes, the survival probability. Exactly.
And the what's WRT?
Is the probability that you have a jump at site I and then at site J at the distance R. So this is already assuming translation, using the translation invariant of our system. Only the distance will matter.
Probably that jump and later another jump.
Yeah, but without any other jumps in between. So you don't have this, and perfect detection, we assume kind of nice detect, some idealized scenario. Yeah, and we cannot see much from this quantity, but also this quantity in the thermodynamic limits, it will just go to zero. So it's not clearly not the right thing to look at. Then if we can extract anything physical from here, different question, but clearly the phi is a quantity that makes sense in the thermodynamic limit. And we can plot it. So just it's basically, there is the definition. What you see that at late times it develops this cusp, this non-analyticity, which is the signal of the spectral transition in the no-click spectrum. But again, this is a very late time. This is even later than what I plotted before. So this would correspond to events with a minuscule probability. It's not observable in the numerical data, and in the experiment with uncertainty, it certainly will not be. For now, this is sort of the what we found. I'm trying to look at now spatial correlations since we have the formula for the distance resolved waiting time. However, the term is subleading, so maybe and this survival probability is a very strong background. Maybe there is a very smart way to extract some information, but that's still a work in progress. Another view is that maybe this is not possible at all to see this transition, and is sort of another manifestation of the kind of post-selection effect, because here this is a linear quantity that we claim can see the transition because this no-click propagator has some information about the monitoring protocol, right? So, I mean, I guess there is no free lunch. Maybe this can be an interpretation, depends how much you think the post-selection barrier can be overcome or not. Say. So to conclude, I would say these measurement-use phase transitions, they were more in fashion a couple years ago, but there's still a lot of work to be done, especially in these Hamiltonian monitored systems. I think there is still a lot of interesting questions to ask. Yeah. Then I think there is the severe lack of numerical simulations of these Majorana chain, for example. Like for the U1 case, people were only convinced when there was this large-scale numerics and stuff. So I think this is probably a natural next step for someone with a lot of GPU hours to do. So then what I said before, the waiting time distributions are post-selection free, but this signature is hidden in the long time tail, so it's not observable. Maybe there is a smarter way to try to extract information from these measurement records, but at least these simple analytical things that we could compute were not able to do so. Yeah, and that's it. If you have any question, feel free to ask. Yeah. Yeah.
So I mean, starting to keep the post-selection of the problem very hard task.
No, yeah. some people would say impossible, I would say.
But one possibility is theoretical. Trying to simulate that system by sort of tilting your evolution. There are some.
I mean, these tilted Liouvilleans to get the. Okay.
Yeah. Rare events like.
Mm-hmm. That's it. The full counting statistics of these jump events and stuff. Yeah, I mean. Mm-hmm. So I briefly took a look at this. There's some, but I didn't find anything easy to compute that showed. But yeah. But the thing with this specific system is that while the Hamiltonian is Gaussian, the full in-blood dynamics is not, because the jump operator is quadratic. And when you tilt it, so the full in-blood dynamics you can still solve, at least depending what you are interested. But like in this, the equations of motion for the correlation matrix still close, so you can simulate it efficiently if you are interested in these occupation rates. But as soon as you tilt it, I think is quite hard. I don't think you can do an exact solution as far as I'm aware. Mm-hmm.
There's an asking because you're doing, yeah, fine. Then you measure and you don't go out for measurements, and then so you on non-Gaussian states, and then you are in trouble.
Yeah, but
the situation of the dynamics.
I'm not sure how to do it for this system, but I know that. So I guess I can just let me go quickly back here. So if you know how the effective Hamiltonian is defined, I guess I didn't put it here, but so the effective Hamiltonian is just the Hamiltonian minus I, the monitoring group, minus I over 2 times the expected value of the dagger jump operator. So for fermions, interestingly, if you consider a jump operator that is proportional to the particle number or to the particle loss, it gives you the same no-click propagator. So this is also another system I looked at, and it seems to have the transition in the same spot. And here you can do this, through third quantization, you can solve this full invariant dynamics. I was looking at it now, but yeah, exactly. But assuming some perfect monitoring, I was also looking maybe at so less rare jump events. So if we go here to the which I guess more similar to this full counting statistics. So if here you introduce some jumps, you average over some jump channels, the speed at which your norm will decay will be much slower. So these events are easier to see. However, from what you mentioned last week, we expect this to wash away also the spectral transition. And there is some work on these full counting statistics, but they find crossovers between different regimes, but I have not seen anyone be able to connect it to measurement-induced phase transitions. Another idea is to try to compute these actually with a replica trick and stuff, and adding normalization to make it nonlinear. But is easier said than done, for sure. And I think you will lose all ability to make precise statements at that point. Maybe you can do some scaling. I mean, numerically, we naturally have access to these quantities. The problem with numerics is you have to discretize time. So if you want very precise waiting time distributions from numerics, you need to make that time step very, very small. And this makes your algorithm scale worse with the systems. I think it goes up to L to the fourth, which, I mean, it's not awful, but yeah, still you cannot do absurd system size unless you have infinite compute. But you naturally have access to these nonlinear quantities, because here I assumed I'm in the steady state, but in practice you can look at the variance of these waiting times between trajectories. I tried to do this, but they weren't, the fluctuations didn't seem large enough to detect anything. Yeah, I think it's quite hard to extract anything from here. Now there's some people trying to do this with AI, for example, for circuits, and I think they are able to do this learnability transition. But there they also have one more information point, which is the incoming information, right? I think trying to extract things from the just once you are in stationary state is quite hard. Maybe it's just somebody with a very good idea needs to come around.
One thing, so, here you work with time, but something that happens stochastically. Are there any approach using a sort of Fourier transform?
Like trying to Fourier transform the whole dynamics, like this stochastic. I don't. You have the issue that the measurement operator is not local in the Fourier base, right? You just have a. Yeah, I mean, I have no clue how to do it. I've not seen anyone look at it. Yeah, this measure, the process also breaks translation invariant. So here I could do analytics because steady state is translation invariant, but yeah, that's some complications. Yeah. Yes, another thing to mention, these sort of tools can be used, for example, for if you have a transition in the steady state of your Lindbladian, these things seem to be able to capture it, at least for some models, like long-range models I've seen. Yeah, if the full Lindbladian has a transition, but that's not what we were trying to look at. But yeah, but for properties of the steady state, seems more, I mean, makes sense that you'll be more sensitive to it.
Have you thought of making measurements more sparse? Keeping the translation environment.
Now doing even sides or every 4 sides.
And as you can see whether you get some different effects. Because you don't expect.
Yeah, if it's very, very sparse. No, I've not. I've played around a bit with this in the U1 symmetric case, because if you make this monitoring, for example, on even sites, your Hamiltonian can have a spectral transition. It will not be trivial anymore. But I mean, I don't think there is a which one, the U1. Yeah, I mean, in these cases where you can sort of engineer your no-click Hamiltonian to have a spectral transition, so I could have put here another paper where they do U1 with this weird measurement operators, like on 2 sides simultaneously, but nearest neighbor, so still local. And they see that there is, when the gap closes of the imaginary part, they see different behaviors, like super diffusion, or the information spreads much faster, these type of things, but it's not never extended. I think it's maybe, I mean, there are people here, I think Federico, for example, we work a lot with non-Hermitian U1 systems, right? I think it's not possible to have an extended phase with a gapless imaginary part, right? Or like you either have a full, if it's PT symmetric, you either have full imaginary or full real, right? Or with a constant. So you cannot have this type of richer phase diagram in the no-click Hamiltonian. I think it's I read your paper of the local measurement. I was thinking a bit about it, but I didn't have a clear idea to pursue. So I didn't explore it too much. Yeah. Yes. Thank you, and sorry for holding you a bit longer.